it away, Guillermo.
Okay, thank you. Thank you very much, Volkan. Well, first of all, I would like to thank both Volkan and Jan for organizing such a wonderful workshop from the EPFL side, and also the organizers from the Japanese one. Because as Volkan said, I mean, I think as young researchers who started our career during the pandemic, we haven't really had that many opportunities to present in front of such a large crowd in person, and definitely internationally there have been also many problems. So I'm extremely grateful for the invitation. So, and actually I'm also pretty grateful to Yingfen, who actually made all the introduction for my talk, because I will keep continuing on the topic of adversarial robustness. And well, in general, in my work, what I try to do is analyze and understand from an empirical perspective some very weird deep learning phenomena that happen with neural networks with the objective to try to understand them better. And in today's talk, I will talk about adversarial robustness, and in particular, one very sneaky and surprising bug that happens when you try to train a neural network to be robust using adversarial training, and you try to do it in a sloppy way and you do it fast. Then suddenly weird dynamics start to appear, and this phenomenon of catastrophic overfitting happens. So today I will try to introduce you to this quite fascinating phenomenon, and I will try to explain you why it happens and what is the cause for this, because even though we know this was happening before, we didn't really understand what was the cause for it. And in particular, the main objective of today's talk will be to try to convince you that catastrophic overfitting is nothing else but some reflection of the properties of the data. So we will try to understand a bit what is the structure of our data and how it influences our deep models. So, okay, as I said, like I will just, this doesn't really work. Oh yeah, okay, thank you. So as I said, like I will just go very quickly. We're still in the context of adversarial robustness, where we have models which are extremely accurate and they can predict the label of an image with extreme precision. But there is always some way that we can optimize some small perturbation, such that when we add it, even though this will render some image which is completely indistinguishable from the one we had at the beginning, will completely fool our classifier into thinking that this is a completely different category, right? So this geometrically, what it really means is that almost for any point in our data set, it really doesn't matter which point you pick, and for virtually any model that has been trained using standard procedures, if we draw some epsilon ball around these points, and in practice, if we pick this epsilon to be a very, very, very tiny number, it doesn't really matter what point we pick. There will always be some direction that if we try to find it in this super high dimensional space, will move our point from one side of the boundary to the other side. And this is what we call that the network has been fooled. And this, of course, poses some security threats. It's really kind of like a very clear indication that these models are super brittle. But in my opinion, the main concern about this thing is that it really shows that the way that neural networks see the world, even though it really might seem that they're working perfectly and they're solving a seemingly human task, it's very counterintuitive. So this, to me, is really the main concern about adversarial examples. And this is the reason why we really want to come up with some certain solutions to make these models more human-aligned. And as Yingfen said, the current solution that we have that works the best, at least on a scale that we can really deploy and work with in practice, is adversarial training. So adversarial training, it's another training procedure, alternative to the standard one, where instead of trying to minimize the cross-entropy loss in a classification setting between the output of our model and the labels of our data set, what we try to do is minimize the worst case loss around some epsilon ball around our data, right? So on top of minimizing the loss, we're also introducing an extra maximization problem there, which makes, in general, the dynamics of this problem much, much more complicated, right? Where we go from a minimization problem to a minimax problem. And in practice, the way people approach this problem is by alternatively minimizing the one objective and maximizing the other. So for every batch of data that we get, we try to optimize the problem inside. We try to approximate it using some adversarial attack. And then we feed the result of this adversarial attack to the model that then we solve, like we optimize using backpropagation and standard SGD. And we go from one to the other. And what this means is that while standard training is actually very cheap to compute, and we have managed to scale it up to billions, I think trillions of parameters nowadays, adversarial training, on the other hand, is much, much more expensive. And the reason for why it's so expensive is really that on top of minimizing our model with respect to the parameters, for every batch that we show our model, we need to solve an extra optimization problem, which is this adversarial attack. And again, as Jingfen said, the main adversarial attack that is used in the context of adversarial training is a very elegant algorithm, which is just basically projected gradient descent. It should actually be called projected gradient ascent, because we're maximizing the loss. But anyway, this is what the literature normally refers to. And PGD, in the setting where we're normal, typical one with L infinity constraints, it just basically amounts to taking n steps of gradient ascent while making sure that we satisfy the adversarial constraints of our problem, right? So for every x that we give, we will start following the direction of the gradient, and whenever we get outside our epsilon ball, we will just project it back and move there. Now, the great thing about PGD, sorry, the clicker stopped working. OK. Yeah. So the great thing about PGD is that it really succeeds in fooling the networks, right? Like, we're trying to just approximate the maximization loss that we have there. There should really not be any guarantee that PGD does work. But in practice, if you just take a model, a standardly trained model, and you try to optimize its loss with PGD, you will find that with a very, very high success rate, you will be able to fool the network. So this is really a great attack. It's a very strong one. And if we increase the number of steps that we ask the model to optimize, then we will see that we can always fool the standard networks. Now, the problem with this attack is that it's very expensive because it's a multi-step attack. So if you think that you're doing something like PGD 10, so we're taking 10 steps of PGD, this will increase the cost of training times 11, right? We will take for every step that we had, we will have to do extra 10 steps of gradient ascent for every batch. So this really blows up the cost. So there's really a lot of appeal with trying to do adversarial training, but as long as it's so expensive, people will not use it. So if we really try to be fast, and we say, OK, let's try to optimize this, maybe we will not get as much robustness, then the first thing that you can think of is, like, why don't we reduce this number of steps n to the point that we can fool the network and at the same time, like, keep going, right? So the first thing that you could say is, like, actually, and this is actually quite nice, is that at n equal 1, right, we can still fool the networks. And this is what FGSM as an attack does. It's really just PGD with one single step. And the way to visualize what this algorithm in practice is doing is that it's just assuming that because we're on a very close region of our point, right, like epsilon is very small, then probably our first linear approximation of our loss, it's quite accurate, right? Quite accurate to the point that if we solve this, this problem, which has a nice closed form expression, we will probably be able to fool the network. And in practice, as I said, PGD does work, but FGSM also does work, right? So if you just take a standard model and you try to attack it with FGSM, in only one step more, you will succeed to fool the network, which is great, right? Because this is a single step attack. But now in practice, people don't really use FGSM. And the reason why people don't use FGSM is because catastrophic overfitting. And here's where this bug comes in, right? In a normal training run, if you're trying to do adversarial training and you're using PGD, so normally people use PGD 10, then what you see is that on the training set, the performance against your attack, so we're showing examples to the network, and we're always attacking them with PGD10, we see that during training, the network gains robustness, right? Like, at the beginning, it has 0% training attack accuracy, but as we show more and more examples, then eventually the network learns to move the boundaries in a way that it will actually manage to make many, many points far away from the boundary, right? This, of course, happens in the training set, but what we want is that this generalizes to the test set. And in robustness in general, what we want is that we generalize to also stronger attacks. So what people normally do is that instead of just evaluating the model with PGD10, they evaluate it with something much stronger, like typically PGD50. Right? So we're attacking with PGD10 during training, but in evaluation, we're seeing the performance at PGD50. And what you see in a normal run is that actually these models generalize their robustness also in the test set, which is quite nice, right? This is really what we want. But this is what happens when you do the same with FGSM. With FGSM, if you start checking what happens at the beginning of training, everything seems to go right. At the beginning of training, our training attack accuracy, where in this case our attack is FGSM, is a much weaker attack, is actually slowly improving, as you would expect, from some normal training run. And the nice thing is, like, even if we're using just one iteration of PGD to fool our model during training, if we evaluate during tests with PGD50, we see that also the model is gaining some non-trivial accuracy. In fact, we see that it's pretty on par with PGD10. Which seems like to give you a lot of hope that we can do fast adversarial training. Now, the surprising thing happens at epoch 15, where somehow, really, we don't really know why, the model completely snaps. And in just 1, 2, 3 batches, and I'm really talking about batches of data, the model goes from having something like 50% robustness against FGSM to something like 80, 90, and goes up all the way up to 100%. And this is super, super fast, right? So it seems that the model is incredibly robust against FGSM, but the moment we test it on PGD50, then you see that the performance completely drops to 0. So in these 2 batches, suddenly the model, without any real clear notice, completely went from having something which was kind of robust to no robustness at all on PGD, but a lot of robustness on FGSM. And this is extremely weird. Because it's not only weird that this happens on all data sets, really, and for almost any model that you can think of, but it's very weird because it doesn't happen for every epsilon. In fact, if you try to make a model robust against a very small epsilon, right, FGSM actually works. Like, I can use fast adversarial training to make a model robust to epsilon 2, but there seems to be that for every model and for every data set, there's some threshold of epsilon at which suddenly this catastrophic overfitting starts to happen. It really is a binary effect. Like, there is this cutoff threshold, and this makes a phase transition in our model that makes it from actually succeeding in making the model robust to actually suffer from catastrophic overfitting. And for every model and for every data set, there seems to be a different cutoff. But the moment you reach this cutoff, you will not be able to use FGSM anymore. So this is very strange. And this has attracted a lot of attention. Like, in practice, there's many people that are trying to make adversarial training fast. So a lot of people have really tried to make these type of techniques work. And there are really a couple of tricks that you can do to make FGSM actually work. And I think the most well-known one was actually developed in this house. It was developed by some people here at EPFL. It's based on a really nice observation, which is that when catastrophic overfitting happens, then it seems that if you check the direction of the gradients with respect to the input around your training data, you will see that all the gradients become very misaligned, which is kind of like a symptom that the model is becoming highly nonlinear. So what they say is that actually this only happens for the models that go through catastrophic overfitting. And in the PGD models, the gradients are aligned. So their claim is that catastrophic overfitting is happening because actually we're training with an epsilon which is so large that this linear approximation, the first order tailored approximation that we're making to the model, will not work. So they say the reason why it happens at certain epsilons is because at some point this linear approximation is not valid. So the model would just basically break FGSM by becoming highly nonlinear. So the way that you can make this work is by adding a regularizer that encourages the model to become linear again. So if you add this regularizer, you will see that you can still work with FGSM. There are, however, other types of techniques. Can somebody move that? It doesn't really work. No. OK. other types of techniques, which are based on the idea that this is an overfitting phenomenon, right? Like it seems that the model is really overfitting to FGSM attacks. And when we have overfitting, what we want is to show more data to the model. So what they say is like, let's do some data augmentation so that instead of training directly by attacking the points at X, we will add some diversity to our data by perturbing it with random noise and evaluate on this other positions, right? And actually, this works. It seems to really work at no cost in training time, and there's really many more. And it seems that there's really some battle now to try to push this frontier at the cutoff where the epsilon happens. And there's many techniques to do this. Some of them succeed more, some of them succeed less. But the main issue that we have here is that we really don't understand why they work. We not only don't understand how they work, but we also don't know why catastrophic overfitting happens in the first place. I mean, the explanation given by the people that developed Guillermo seems kind of reasonable, but it doesn't really explain why these other techniques also work, and it doesn't really explain why is it so sudden. Why suddenly the model goes through this phase, and it is very strange, the dynamics of the system. So in this project, what we try to say is like, OK, can we try to understand what causes catastrophic overfitting? What is the reason for this sudden nonlinear increase that breaks FGSM? And in particular, the standpoint that we took was, OK, if we try to analyze catastrophic overfitting by just exploring the parameters that lead to catastrophic overfitting in the wild, like the situations where we know it happens, it might be very hard to really infer some causal connection, right? Like, we will probably just identify some correlation. So what we said is like, is there any way that we can induce catastrophic overfitting artificially? Just say, take some situation, like a small epsilon, the smallest epsilon we can think of, and be able to induce catastrophic overfitting. If we can do this, then it means that we have identified the cause for this phenomenon, right? So really, this project was all about inducing this bug. And when we were trying to do this, we were thinking about three main ideas. We had three main things in mind. The first one is that really you need to understand that neural networks do not want to be robust. Like the standard default way that a neural network will try to solve a problem will always be a non-robust solution. In fact, if you start doing adversarial training and then suddenly you stop attacking the model during training, the model will start losing all the robustness. This is really an indication that the inductive bias of the model is really favoring the non-robust solutions over the robust solutions. So we had kind of this in mind. And the other thing we had in mind is that when catastrophic overfitting happens, there's barely anything that happens to the clean accuracy. Like the plots that I showed you before were checking the robustness of the model. They were checking what happens when you attack the model. But if you actually check what is the clean accuracy, the accuracy when you don't attack the model, after catastrophic overfitting, the clean accuracy actually increases. Like the model becomes more accurate when catastrophic overfitting happens, which gives you sort of like a weird paradox, because the models that have gone over catastrophic overfitting are kind of in between a robust and a non-robust model. They're as accurate as a clean model, but they cannot be perturbed fooled with FGSM, but they can be fooled with PGT. So there seems to be some weird in-between thing happening there that allows the model to also use catastrophic overfitting to improve its clean accuracy. And then the final idea that was kind of floating in our mind was this widely, I think, now accepted theory of why adversarial examples happen in the first place, which is that the adversarial examples are nothing else but some reflection of some existence of non-robust features and weird non-human ways to solve our problems, right? So this is a very well-known paper that claims this, right? Adversarial examples are just features in your data. So with this in mind, we thought, could it be that in the end, what causes catastrophic overfitting is just the existence of certain types of non-robust features in our data? Could it be that really, if you have certain types of structures in your data, this is the thing that leads to catastrophic overfitting? So with this in mind, we said, OK, if this is true, then there has to be a way to just take any data set and some setting where catastrophic overfitting doesn't happen and modify it by introducing our data and see what happens, and see if we can induce catastrophic overfitting. So what we said is, OK, let's take our data set. Let's create some bunch of discriminative signals, some features which are very, very easy to pick up. In particular, we just pick one pattern for every class in our data set, and let's add it additively to our model. By doing this, what we're doing is basically constructing some sort of hybrid model, which has some features from our original data set, plus some other features which are highly discriminative. But depending on the parameter beta, they will be very robust if we make beta very, very large. So the model will try to identify them very easily. But as long as we make beta very small, in particular, if we make beta smaller than epsilon, this will not be enough to solve a robust problem. So we basically took this data set, and we evaluated the performance of adversarial adversarial training with FGSM on many different setups with different betas and different epsilons. And what we identified is that actually there seems to be some relationship between beta and epsilon that can induce catastrophic overfitting. So for instance, look at the green curve on the plot of the left. In the plot of the left, at beta equals 0, we're just training with the original data set. We're not adding any features. And as we can see, the robust accuracy at the end of training is not 0. The model has not suffered catastrophic overfitting, although it was trained with FGSM. But as we start increasing beta, so we're injecting more and more of this discriminative feature, we see that there's a certain point, which is the point where beta becomes slightly larger than epsilon, where the performance drops to 0. And it drops to 0 for a while. And the moment we increase beta a lot, then the model goes up, and its performance, even robustly, goes to 100%. So this really indicates that the model is learning the discriminative features, but there's something happening in this phase transition. And this, of course, happens at different epsilons. And the funny thing is that it happens at epsilons where it doesn't happen normally. So once we had this, OK, this answers positively our answer, that our question that like catastrophic overfitting is indeed caused by certain features, but because we have this control now on the way that catastrophic overfitting happens, we can experiment and try to understand how it works. So basically, what we did is, like, first of all, check what was the preference of the model. What happens to the model, and which features does the model pick when catastrophic overfitting happens? So here we have a PGD training run, standard training run, and FGSM training run, trained on the same beta epsilon setup, which leads to catastrophic overfitting. And what we see is that for the standard training run, the performance on the data set that we're training on is super high. Like, we see 100% test accuracy, while the performance on CFAR10, which is the original data set that we perturbed on, which doesn't have the extra features, is very, very low. This means that although we're training with both features at the same time, the model is only picking the discriminative ones, the injected ones. On PGD, on the other hand, what we see is that the performance increases on both data sets at the same time. So the model is actually learning something about CFAR, although there's these discriminative features. And this is not surprising, because as we said, when beta is small enough, this will not be enough for the model to be robust. Now, on FGSM, what happens is, like, at the beginning, it follows the same thing as PGD. But the moment that catastrophic overfitting happens, we see that the robust accuracy drops to 0, then it completely forgets about CFAR. It goes back to PGD, to the CFAR ones. So this is the first thing that we can see. The other one is that we can check what happens to the curvature, to the nonlinearity of the model. And what we see is that the model becomes extremely nonlinear, as we expected, the moment catastrophic overfitting happens. But we also see that the nonlinearity increased before. And our theory is that the nonlinearity was increasing before because the model was actually trying to combine the two types of features. It's trying to become more nonlinear to separate the data. And to show this, actually, let me skip this. What we can do is actually check what happens when the model does not need to combine the two types of features. So as I said, our theory is that combining these two types of features requires to extract more features in a nonlinear way, and this induces the model to become nonlinear. So what we can do is try to inject the features in a way where there's no interaction between them. So instead of just adding the data, we will project away all the component in our discriminated set V from the data itself. And when we do that, what we see is that we do not suffer from catastrophic overfitting. If there's no interaction between the two, like the discriminative features that we inject and the original features are in orthogonal spaces, then we do not see catastrophic overfitting happening. There's no dip at any beta. There's only two sets, the case where you learn CFAR and the case when you learn the other features. And what's more, it's like actually we check the curvature, so we see the curvature on the left. We see that in the orthogonal injection case, the curvature does not increase. So what this really means is that, as I said, catastrophic overfitting is actually induced by a feature. But the other thing is that now, by having done these experiments, we can now create some mechanistic explanation on why it happens. And with this, I will close. So basically, just to wrap up, what we have seen is that for catastrophic overfitting to happen, there has to be three sort of mechanisms that have to happen together. The first one is that there has to be some sort of way that the robust solutions need to combine the easy and the hard solutions, and the hard features, right? When this happens, we have seen that the model will try to combine the two types of features in a way that will have to increase its nonlinearity. And the thing is, the moment you start increasing the nonlinearity, because you're trying to separate these two types of features, you will give the model a shortcut. You will give the signal to the model that if you keep increasing the nonlinearity, there will be a way that you will manage to break FGSM while at the same time being very accurate by just learning the easy features. And this is really what leads to catastrophic overfitting and explains why it's so sudden. The model has just found some learning shortcut that makes it actually solve the problem in an optimal way, which is be robust to FGSM. This is the thing you're asking me about. And at the same time, be highly accurate. And well, I think with this, I can stop. And yeah, I will be open to questions.
Maybe we'll take a question if anybody has one. Go ahead. Come here.
Hey, thanks for your talk. I was wondering about, I think it was on slide 6, where you had this comparison between the training loss and the test loss. You were saying that exactly here where you see the drop, the robustness drops in terms of the test with PGG, but there's sort of two things happening here. Both the attack is changed and also the distribution is changed. It's now test. So what is the conclusion? Do you see this catastrophic overfitting even on train if you run PGG? Yeah,
you actually do see it in PGD. So what happens is, like, and in test, you also see that you're robust to FGSM. So you're basically robust to FGSM no matter where your data lies, and you're non-robust to PGD almost anywhere. So it doesn't really matter test or train, you just see the same effect.
Okay, thanks.
Yeah.
Other questions? Maybe I have a quick one. So normally the way I think about this is that you're actually doing some sort of finite sum minimization. Now, to get the gradient for your finite sum from the max term, you need to get an optimal solution to the max, then take the gradient. So when you just do one fast sign attack, this means that as epsilon grows, you're actually not getting the gradient, but instead you're maybe doing just simple perturbations, right? So then isn't it normal that your clean accuracy should start going up, whereas you're no longer robust because you're not solving the robust optimization problem?
Yes, that's actually right. It really means that the model doesn't need to become robust. It can just solve the clean problem. Yeah. It's the same as adding random Gaussian noise. It actually happens. But the thing is, the interesting thing is, how can the model keep this nonlinearity high while at the same time, so it has to fool FGSM. Like at the beginning of training, this doesn't happen. If what you were saying was as simple as if you make epsilon very large, then basically your attack doesn't work ever. Then
you're not getting the gradient to this maximization.
But why does you gain? Like, why do you gain robustness at the beginning? Like, you're actually gaining robustness half during training, and you gain completely non-trivial robustness. So the attack is working at the beginning. And
so perhaps at the beginning the approximation is good enough. But
exactly.
When you're trying to go to the solution of the original problem, you need to be solving it accurately. Initially, maybe it doesn't matter.
Okay, yeah, exactly. But the question is what happens and in which situations this is accurate and in which situations it's not.
Okay, so maybe we stop here. Thank you.